We're picking up today talking about empirical and molecular formulas, looking at what those differences are between those and how we can actually calculate them or determine what they are from data. And so that's really what they are. These are different ways that we can calculate or determine what the formula is going to be for an ionic compound or a covalent compound from data that we get from an experiment, from analysis of a compound, of a sample. To start off though, before we can really look at empirical and molecular formula, we have to look at percent composition. And basically all percent composition is, it's just the ratio of the mass of each element in a sample or in a compound to the total mass of your compound. So it's always a part over a whole type situation as we look at a percentage. And so that's where we want to find out what percent of each element makes up a compound. So there are two different ways that we can find percent composition. There's two different methods. The first method is what we say it's from a formula of a compound. If we're given a formula, we can find out what the percent composition is going to be. And basically what we do is this. We find the molar mass of the compound like we found molar mass before. Then we take each total mass of the element, of its molar mass or atomic weight of the element times the number of atoms there are. We take that product and we divide that by the molar mass of your compound. And then we multiply by 100 to get your percentage. And we're going to see this on the next slide. So I want to find the percent composition of sodium bicarbonate or baking soda. Sodium hydrogen carbonate is another way we can say that. So again, we start off and we find the molar mass. So we write down each element that's present: sodium, hydrogen, carbon, and oxygen. We write down their atomic weights, how many atoms there are, and we get the total for each atom. So 23, 1, 12, and 48 for oxygen. We add those together and we get 84. Since a percentage is always a part over a whole, your elements will be the parts, and the total will be the part. The molar mass overall is your whole. So all we're going to do is we're going to divide each of the total values, 23 grams per mole by 84 grams per mole, that will give us our percentage for sodium. And that's what we see on our next slide. So I've done that here. I've taken my molar mass. I've taken my percent of my sodium is going to equal to how much sodium there is divided by the overall total mass, 84, times 100 is 27.4% sodium. Same for hydrogen. 1 divided by 84 times 100 would be 1.2% hydrogen. 12 divided by 84 to get 14.3% carbon. And 16 divided by 84, actually it should be 48 divided by 84, but it's still 48%, or 57%. I was going to change that before, so let's do that now. 48. There we go. That looks better, right? Okay, and that's how we get our percentage. That's basically all we do for percent composition, especially from a formula. The second method is we may be given from mass data. We may be given, okay, we did an analysis, whether it's atomic absorption, it's infrared spectrometry, it's nuclear magnetic resonance, whatever that different way is that we're kind of approaching from mass spec data, that we're getting the data, we may be given how much data. But the same concept is going to hold true. It's always going to be a part divided by a whole. How much of each element there is divided by what the whole mass of your compound is. So your percentage by mass for an element is always, as I said, the mass of the element divided by the mass of the sample times 100%. The percentage just gives us percentage as a value at the end. So here's our example. If I have 35.07 grams of phosphorus reacting with oxygen, we form a 71 gram sample of phosphorus oxide. What's the percent composition? Okay, so basically from the law of conservation, we know that the mass of reactants must equal the mass of your products. So if I have 35.07 grams of phosphorus, I can figure out how much oxygen there must be to get 71 grams of phosphorus oxide. It'd just be the 71 minus 35.07 to give us 35.93 grams of oxygen. Okay, so this is how much I have: 35.07 grams of phosphorus, 35.93 grams of oxygen. Now I can find my percentages because it's a part divided by a whole. And so that's going to be my mass of my phosphorus divided by the mass of the compound, the whole sample. And then for oxygen, the same thing, 35.93 grams of oxygen divided by 71 grams of your compound. multiply by 100%, and we have our percentages by mass of each substance. 49.4% phosphorus, 50.6% oxygen. Okay, so again, it's just that part divided by the whole. For two different methods, both ways basically do the same thing. We have to do a little bit more work if you're given a formula because you actually have to find the molar mass. If you're given a sample like this, you don't have to do anything but find the percentages. Okay, that means we're up to then empirical formulas. As we look at empirical formulas, what we're talking about are basically a formula that has the simplest whole number ratio of elements in it. It's what we always use to represent ionic compounds. Formulas for ionic compounds are always empirical formulas. They're always at simplest whole number ratio because they exist in crystal lattices, and in that crystal lattice there can be millions and billions of each atom in it. And we don't write the formulas with all those values, we write what that simplest whole number ratio is. Covalent compounds, though, can be empirical formulas, but they don't have to be. They may be molecular formulas too, which we're going to talk about after we talk about empirical formulas. But again, we have two different ways that we can find empirical formulas. There's two methods based on what our data is. We can either have from percent composition data. If we're given something about the percent composition, then we can find the empirical formula. We can also find empirical formula from mass data, like the second part of percent compositions. So we take a look first of all at mass data, or actually look at percent composition first. The important thing, though, is to remember in this case that's important to determine empirical or molecular formulas is two things. We've talked about this in class a couple times, but we're going to hit it again here. The subscripts in a formula tell you two things. So if I have H2O, that can either mean that I have in one molecule of water, I'm going to have two hydrogen atoms and one oxygen atom. But those numbers also, those subscripts also tell us numbers of moles. So if I had 1 mole of water, I would have 2 moles of hydrogen and 1 mole of oxygen. See how those numbers are exactly the same, we just changed the quantity. Atoms are moles, atoms are moles. Those are your keys to finding empirical formulas, knowing those two things. Okay, from percent composition data, it's the moles that let us do the work. Since formulas are ratios of moles, and atoms as well. In both types of the problems that we're going to be looking at, what we want to do is find out how many moles of our substance do we have. And that's the first key, find the number of moles of our substances. Then we're going to be able to write a formula that has that number of moles in it. Doesn't matter right away that it's not a whole number or not. Okay, I take and find out how many moles I'm given, whether it's from grams or from my percent composition. Once I have the moles, since the formula also tells me the number of atoms, I can't have decimal numbers of atoms. So to get rid of those decimal numbers of atoms, we're going to divide all the values of those moles we had by the smallest value. And that's going to give us, most likely, more than oftentimes, give us a whole number or something very close to a whole number. And we can round to the nearest whole number if we're within a few hundredths of the gram. If it's like 1.5 or 1.33 or something like that, we're not close enough to round. We have to do something a little bit more, and you're going to see an example of that shortly. But again, dividing by that smallest number of moles is going to give us the simplest whole number ratio. So we find the moles of each element, we write a formula with those numbers of moles in it, we divide by what's the smallest number of moles was going to be. And it's the same for both cases, we just have a little bit different process to deal with at the beginning. After the beginning part, for both types, it's the same. So if I start with percent composition data, I want to find the empirical formula for a compound that has this composition: 48.64% carbon, 8.16% hydrogen, and 43.2% oxygen. Where am I going to start? How am I going to find the number of moles here? Because that's what we said, find the number of moles of each element. The very first thing that we always do with empirical formulas is we're going to make it as easy as possible. So what we're going to do is we're going to start off and we're going to assume that I have 100 grams of compound. Because if I have 100 grams of compound and it's 48.64% carbon, I know how much carbon I have. I can assume any amount, but 100 grams is very simple because the number of grams of each compound you will have, or each element you'll have in a compound, equals the percentage. So that means I'm going to have, if I assume 100 grams of compound, I'm going to have 48.64 grams of carbon. Here's my There we go. Then we're going to have 8.16 grams of hydrogen on the left side here. And we're going to have 43.20 grams of oxygen. Okay? And what we said, the first step to do is once we assume that we have that number of grams, find the moles. Moles is equal to grams over molar mass for each case, for each element. So I take my formula mass, or how many grams of carbon I have, divide by the atomic weight of that element. Okay? In this case, we're finding the moles of the element, so we have to take it by the molar mass of what their atomic weight of what that element is. So I have 4.05 grams of carbon, 8.16 divided by 1 because that's the atomic weight of hydrogen is 8.16 moles of hydrogen, and 43.20 grams of oxygen divided by 16, which is the atomic weight of oxygen, is 2.70 moles. Okay, that's step 1. We found the moles. Step 2 is write a formula with those numbers of moles in it. So I can write a formula that should look like this. C 1.5 H3O, because those are the numbers we just had. Now that 1.5, we said we can change these values if we're around them, if we're within a few hundredths. 1.5 is not within a few hundredths. We can't get rid of that by rounding it. We can't round that up to 2 or down to 1. So instead, we have to deal with that value by, first of all, the easiest thing to do is change it to an improper fraction. So I'm going to change that to be 3 halves, 3 and 0. Now what I can do then is, since I have to have that's my number of moles, and that's fine, but since the formula also tells me number of atoms, I can't have a decimal or fractional number of atoms, so I have to get rid of that fraction, which we kind of saw when we did balancing equations with oxygen. All we need to do is multiply everything by the LCD, the least common denominator, in this case, which is 2. So if I multiply everything by 2, then that will give me C3H6O2, which is now my empirical formula. So 1 mole of this compound would have 3 moles of hydrogen, 6 moles of 3 moles of carbon, 6 moles of hydrogen, 2 moles of oxygen. Or 1 molecule of this compound with 3 atoms of carbon, 6 atoms of hydrogen, 2 atoms of oxygen. Okay, so we found the moles of each element, and then we wrote a formula with those number of moles and divided by the smallest number. Now we can do this exact same process, but through mass data. It's exactly the same process, but the only difference is we don't have to assume that we have 100 grams of compound. We already have a sample, so all we're going to do is find the moles for the number of grams of compound that they actually told us. So like the example we did for percent composition, we had the 35.07 grams of phosphorus. All I have to do is find out what the percentage of, or how many moles of phosphorus that would be. 35.07 divided by the atomic weight of phosphorus, which is 31. Okay, that's going to be my number of moles. And I do the same for the oxygen. 35.93 divided by 16, that's my number of moles. Write the formula with those moles in it, divide by the smallest, you got your empirical formula. Okay, so from mass data, it's even a little bit simpler because you don't have to assume anything. You already have the mass, just find your moles. So I didn't do an example of that. Now, molecular formulas are the last topic. And in this case, we're looking at covalent compounds. And covalent compounds can be either empirical or molecular formulas, because we're an ionic compound, a molecule or ionic compound's in a crystal, and it can have millions or billions of the atoms in it, and it's still the same substance. Covalent compounds exist in molecules. And so in the molecular formula, we're looking at a formula where the simplest whole number ratio may not be the actual molecule. Different molecules can have the same simplest whole number ratio, but the molecule itself will have different numbers of atoms in it. Okay, so molecules are single units, and a different ratio, or the same ratio but a different number of atoms, is a different molecule. It's a different compound completely. So that's basically the biggest thing. We can have a different ratio in our compounds, and it's going to be a different compound, which we'll see right here now. I'll show you what we mean by this case. So NO2 is nitrogen dioxide. That's one of the byproducts that comes out of burning gasoline, for example, in your car. It's not a real great thing to have around. N2O4 has the exact same ratio. So if we reduced N2O4 down to NO2, it looks like it's the same substance, but N2O4 is a different compound completely. It's made up as N2O4. It does not have the same chemical and physical properties. It's called hydrazine, and it's used as rocket fuel. So very different substances that have the same simplest whole number ratio. The first one, NO2, its empirical formula and molecular formula are the same thing. Hydrazine has a molecular formula to show what the actual compound is. And there go my lights again. I know that's funny. Okay. Now, to find a molecular formula is pretty straightforward. We're going to first of all do what we did to find the empirical formula. Everything is the same so far. Find your empirical formula by one of those two methods. Once you have the empirical formula, then in the problem you will be given the molar mass of the compound. You will know what that molar mass is. Without that, you can't find out your molecular formula. And the molecular formula will always be a multiple of your empirical formula. So either be 1 times, 2 times, 3 times, 4 times, however many times bigger than the empirical formula that it will be. So what we're going to do is we're going to take our empirical formula that we just found for your element, we're going to put it in parentheses, put an X outside the parentheses, and set that equal to the molar mass of your compound. We're going to find the molar mass of our empirical formula. So we're going to replace the empirical formula, whatever the formula was, with the value, with a molar mass. So we're going to have some number here times X equals another number. And we just solve for X by dividing by what this molar mass in parentheses is. Then what we're going to do is we just take that number that we got for X and we multiply it through the parentheses, through the empirical formula that we had to get our molecular formula. So as an example, let's say that we have an empirical formula of compound is NO2. I just picked that one because it was handy. But we know that the molar mass of this compound is 92 grams per mole. Okay? So what we do is we put NO2 in parentheses with an X outside of it. NO2X equals 92. We find the molar mass of NO2. Nitrogen is 14 times 1 is 14. Oxygen is 16 times 2 is 32. 14 plus 32 is 46. So I replace NO2 with its molar mass. Divide both sides by 46. And I get X equals 2. That's telling me that my molecular formula has double the mass of my empirical formula, or I'm going to have twice the number of atoms. So I put my NO2 back here, and I put a 2 instead of the X. And then I just multiply the 2 through. 2 times 1 is 2 for N2. 2 times 2 is 4 for O4. So NO2, nitrogen dioxide, has a molar mass of 46, but hydrazine, a different compound with the same ratio, has a molar mass of 92. It has a different ratio. Covalent compounds, we don't reduce, remember, what those ratios are like we would with an ionic compound. And just to finish up here, this is for fun. Think you might get a small chuckle out of this, maybe. We'll see you Monday.